Yeah, and our last chapter is about electromagnetic waves. We already discussed a little bit, let's say, when we were discussing the transmission line. Now we are really interested in all the relations we have in electromagnetic fields, and we will focus clearly on wave generation, how are waves generated. That is a very important point for me, that you understand this, that we need accelerated charges. Just moving charges with a constant velocity will not give electromagnetic wave radiation. And how are all these properties we have there, and will at the end even compute for a simple dipole antenna the radiation pattern. Yeah? And you will clearly have in other courses a lot of details, but there you will already use formulas we will derive in order to get all these properties of the antennas. Okay, and we are mainly interested in wave propagation in air, let's say. Yeah? And that will be both if we have guided waves in a structure where they also will be guided by a cylinder or any other structure. We have here optical fiber, for example, or mainly in air. But we will, as you will see, have mainly the situation of linear media, which means we can express everything by a simple constitutive relation for the electric field as well as for the magnetic field. There will be also some investigation in potentials and fields. We already have discussed this general decomposition of any physical field in a solenoidal field, which is a pure vertical field, as the magnetic field, closed field lines, and in an irrotational field, which is a source sink field, which is an electric field due to charge distributions. But we know the electric field can be also a solenoidal field when we think of Faraday's relation written down in differential form by Maxwell. And with this help, it will be even possible to get the general laws of Coulomb and Biot-Savart, which have been done by Jeffimenko, and therefore we have this Jeffimenko equation, which play no important role in practice, but in the understanding. Yeah? Because with this equation, we really get also the dynamic effects in. Yeah? We know we have Biot-Savart for the magnetostatic field, we have Coulomb for the electrostatic field, but we can have these two equations for the real electrodynamic fields, and therefore get the dynamic parts in. And that will also show us then, and will be very helpful when we investigate moving point charges, and we will see that we can decompose our radiating field, let's say, electromagnetic field, in a near field and into a far field. Yeah? And there we will see what is of interest if you design the antennas is clearly also sometimes a near field, but mostly the far field. Yeah? And to know the radiation pattern, because the two antennas, transmitter, receiver, will have clearly some distance. For NFC, for example, we are really interested in the near field, but there wave propagation is not of so big interest, so there Darwin or even the eddy current equations will be sufficient. Okay, and in the last point, we will look at the radiation. We will be always interested in what is the radiated power, yeah, of electromagnetic fields generated by an antenna. What is the clearly the radiation pattern? And then all the details will be not a topic here, but in other courses, you want to have matching and all those things. Okay, now let's start in vacuum, which let's say is more or less also applicable to the case when we are in air. So what we know here is when we write down Maxwell's equation, in the absence of currents and charges. Yeah? That is clear. If you already have generated the waves, we are somewhere in vacuum or in air, and the waves are propagating, so we can set the charge density to 0 and the current density to 0. And we have the very important equations as shown here, where we have the relation between a vortical, so a solenoidal electric field, because a time change in the magnetic field generates a solenoidal electric field that has closed field lines, as we know. We also call it the vortical part. And we have vice versa very nicely. You see the symmetry in this case, that a time-changing electric field also generates a magnetic field, the curl of a magnetic field. Yeah? And here, the time in first equation, the time change of the magnetic field, the curl, the vorticity, speaking of the electric field. Yeah, and both divergence in this case then are 0. This is a standard, as we know. The divergence of B is always 0. But in this case, since we have no charge, is also the divergence of E is 0. And so we see here a nice symmetry, yeah, which we do not have for the full Maxwell's equation when we take into account charges and current densities. Okay, furthermore, what we will use here is this vector identity when you have the curl of a vector field, which means we will here apply this to these two equations. Then you can write it down as the gradient of the divergence, yeah, which in our case will be always 0 for both fields, E and B, since we have these two relations here. And we have the vector Laplacian operating on the magnetic field or on the electric field. Okay, so you see, if you now take on these two equations, let's start with the first equation here. We apply the curl operator. Then you have the curl of the electric field, which we can substitute here, as you can see, by minus the Laplacian of B. Have in mind that actually there will be a minus. And you have the curl of the time derivative. Yeah? But if you look here, when you have the curl of the time derivative, the curl itself can be expressed by the time derivative of the electric field. Yeah? So you will have here a double time derivative on the electric field. And due to this minus, we also have a minus here. And these two minus cancels out, which means at the end, we get here this nice relation that the second order spatial derivative, which is given by the Laplacian operator, is equal to a second order time derivative. And that is the characteristic of a wave equation. As we know, we have periodicity in time due to the time period given by the frequency, and we have periodicity in space given by the wavelength. And as a scaling factor, as you can see, we have here the permittivity and the permeability in vacuum, which is approximately the same in air. And if you do this for the magnetic field, then we also get here the same equation, let's say, characteristic. It is again the second space derivative on the magnetic field and the second time derivative. And we see they nicely, in this sense here, decouple. Yeah? So you have really one equation for the magnetic field and we have one equation for the electric field, but they are interrelated. Yeah? We have to have in mind due to these equations here. We have just done these rearrangements. Okay, so these are actually, if you look now to such an equation, you have no coupling between the x, y, and z component. Yeah? Because you have the Laplacian here on the left-hand side on B, and here the second time derivative. So you have no interaction between the three components. So you even can write now it down as they are three scalar equations. And I have written down here for a scalar G, yeah, which could be the x component of B or the y or the z component of B. And this is, as we know, our typical wave equation in 1D for a scalar quantity. And this part, what we have here, is related to the speed of light. And the speed of light, as we know, is 1 over the square root of the permittivity scaled by the permeability, as we are now here in vacuum, and has this value of 3 multiplied by 10 to the power of 8 meters per second. Yeah, and if we remember what we have discussed in the transmission line, we already know the general solution, and the general solution can be expressed by a function of xi, which could be now with this index I, x, y, or z, plus minus ct, where c is the speed we have. In our case, c would be then exactly c0, just in a general case. Okay, and we get here then this solution where with the argument minus, we have a wave propagating in positive xi direction, yeah. So the minus will be a wave propagation in positive xi direction. And the plus just in negative direction. That we discussed there on transmission line, where we just had one space coordinates, when you remember the space coordinate along the conductor. Yeah, and we clearly have the same relations also here. I just have written it down, that we have here this wave number, not written here, but we know it is the wave number, which is related, and that is the important part, to the wavelengths, and we could simply compute the wavelengths by the speed of the wave over the frequency. Yeah, so the higher the frequency we have, the lower our wavelengths. And that is exactly the same also in acoustics, where we have just longitudinal waves. And you already know that electromagnetic waves are transversal waves. Okay, so we have our general equations for the electric field and for the magnetic field, and we have the relations between frequency and wavelengths and our wave number, and even have the general solution for each component there. Yeah, here is just a table to see the type of wave. We have the frequency and the wavelengths, and here especially concerning the colors with wavelengths and frequency from near ultraviolet to near infrared. Okay, so let's assume we have now a traveling wave in z direction. Yeah, and you know what we also have done in the transmission line. Mostly for wave propagation, you are interested in the steady state solution. Yeah, we are not interested in this sense that first we need that the waves are generated, they travel along with the characteristic frequency. So we go to the frequency domain, or let's say we make this frequency ansatz, where we have our complex value of the electric field, and we always know in reality, we are always in time domain. That is just a mathematical construction. Taking the real part gives us just a time domain solution. And here, as you can see, we have here a E underline 0, which are amplitude, which can have amplitude and phase. Therefore, it's again a complex number. This is due, the underline always is the notation to have a complex number here. And we take this exponential function, as we also have done in the case of the transmission line, and you are used to this, where we have omega t minus kz. Yeah, that is the same. It is such an argument. Now, since it is propagating in z direction, we have omega t minus kz. Yeah, and minus because it's propagating in positive z direction. And the same ansatz clearly we will do here for the magnetic field. Okay, so they will have any amplitude and constant amplitude here, and we will see the amplitude will be really constant. It will change when we have lossy material. We will also discuss. Here we will start with the case that we have no losses, and it is a plane wave going in z direction. Yeah, here explicitly again, they have complex amplitudes, so they have a peak value or root mean square value and a phase. Okay, now if we put this in to these two equations, which we call a little bit the constraint equations, yeah, because we know that the divergence of B has to be 0 and the divergence of E has to be 0. Then what we get out is that they have no z component. So this B naught and E naught has no z component. Why? So I go back here. So that was our ansatz. Yeah? Our ansatz is in this sense, we have electric field being a function of z and t. Both we see in the exponent of the exponential function, and these are constant amplitudes. Yeah? And since we know we have here a transversal wave, we will have E naught and B naught being somewhere in the xy domain, yeah, having a constant amplitude and traveling in z direction. Now, if you substitute, and you have to substitute this whole ansatz, yeah, the whole ansatz, into this equation here, for example, yeah. So you have then the space derivatives with respect to x, y, and z, and we all know that when you have this exponential function, you have a space derivative, then it's again the exponential function with the inner derivative. Yeah, but this exponential function is just a function of the z coordinate. Yeah, and these constants here are constants. Yeah, they can have any amplitude. So if you take the derivative of a constant, so perhaps I rewrite it here. As we know, it is dp x dx plus dp y dy plus dp z dz equals 0. So, and that was our PDE, and perhaps in I make it in green to see it really. Yeah, I make here this underline because we take our ansatz as written here. Yeah, we take here this E underline as well as this B underline. Now we have divergence of B. So in this case, the derivative with respect to x, yeah, will be 0 for this term, yeah, but it will be also 0 for here. I have to look. It will be also 0 for this term. They are constants, yeah. So we have here this being 0. We have this being 0. Yeah, and here we would have a B0 set still underline. It's not. I write it better. So that would be B0 set, the underline, because it's a constant. Yeah, with the product rule, we know that this is 0, but we have here the dependency on z. Yeah, so it would be this exponential function. Yeah, but the inner derivative would be minus k. Yeah? Okay, so we would have here, I write it here, minus k, and we have here our exponential function, and that has to be 0. Yeah, so it is clear k will not be 0, otherwise you have no wave propagation. It is our wave number. So B0 set has to be 0. Yeah? So okay. Now we want to get the relation between E and B. Yeah, that is for us of importance. And there we can use Faraday's law, where we have this relation. So we have to take the curl of E and the time derivative of B. And again, what we substitute is our ansatz we have here. Yeah, we know we have a constant E0, which has just the x and y component, because the z component has to be 0 according to this constraint here. The same is for the magnetic field B, where we have this ansatz, and we have a B0, which has just the x and the y component, because the z component due to the constant has to be 0, but they are constants. Yeah. Now, if I've explicitly written it down, this is our nabla operator cross product with this part here. The exponential function will cancel out, yeah, as we know, because you will have it here as well as here, and so it cancels out. Now, if you take here the derivatives with for the x component, you know, or you can write it as a determinant, but what I do it always, you know, you cancel the first line, and then you have the derivative of 0, okay, will be 0, and the derivative of this part here, where you have this exponential function, yeah, because the derivative of E0 will be 0, but we have this exponential function giving us an inner derivative which is minus jk. But you know, it is here this term minus this term. Yeah? Therefore, we have plus jk e not y, the y component. Yeah, and then if we go to the y component of the curl of E, we cancel out this one. So we again have this minus this, but don't forget, it is the second line. We have to multiply with minus 1. That is why we get here a minus jk. On the left-hand side, it's a little bit easier, let's say, because we just have to do the time derivative. If we look at our ansatz, the time derivative of B, just this term, we have to do the time derivative. This is constant in time as well as in space. So the time derivative always just gives us the inner derivative being j omega. Yeah? And since we have the minus here, we we should not forget it. It's j omega x component, j omega y component, nothing else. If you combine this, then you will see that you get this relation here. It is clear because you can divide by j and you divide by omega. So you will have here on this side always k over omega, also here k over omega, and it will give us here then the unit vector in z direction cross product with E0. Which means at the end that these two components, B0 and E0, having a direction, will be orthogonal to each. And we have, when we take the absolute value, we have the nice relation that the scaling is just the speed of sound you have in your medium. We have chosen here vacuum. So B naught as an amplitude is just 1 over C0 E naught. Yeah, and as you know, in time domain, which is actually the correct domain, we just have used this frequency domain to get this relation easier. And we are interested in the steady state case is to take from our total ansatz, as written here, the real part. And as we know, that gives us then the amplitude of the electric field cosine. Okay, and I have forgotten to exchange this. Okay. I don't know what is in your version. Yeah, you have to exchange this. Yeah, because we have made the ansatz as omega t minus kz. There could be some additional things I have forgot to substitute, because the American way is always to use as an argument key z minus omega t, but as and the European is different. Yeah, it is always omega t minus kx, but you can do it as you want. But I wanted to keep, as we have introduced for the transmission line, if you look back, and I have also discussed with my co-workers, and they told that in the other courses you also have this ansatz. Yeah, we have the ansatz omega t minus k and the coordinate, and not k and the coordinate minus omega t. Okay, so we just have to exchange this. Yeah, and if you look here to the right hand side, then what you see here is exactly the following. For this simple case, yeah, we have a lossless material, we have a wave propagating in z direction, we have the electric field in y direction, the magnetic field in x direction. No, sorry, the magnetic field, this is B naught, I should write here. In y direction, and the electric field in x direction. There is no phase shift. They have, if there is a phase shift, they have the same phase, because it's lossless. Will be different if we have a lossy material, and they are orthogonal. Yeah? So we see it is a typical transversal wave where within the plane you have the B and the E component, or the B and the E field being orthogonal, and they propagate in z direction if this is z direction. And very importantly is that we can express, even concerning the direction, B naught here by this nice relation with the propagation direction, which is the unit vector in z direction, that is the propagation direction, and that is the vectorial electric field. Yeah, Also for plane waves, they do not have to go in Z, X or Y direction. They can go in any direction, and therefore we introduce here a general unit polarization vector. We call it EP. And we have the propagation wave vector, which is K, which was in our case EZ, yeah, because it's going in Z direction, but we can make it in any direction in our three-dimensional space. And then you see we express the electric field by this polarization vector. The polarization vector is just the unit vector of the electric field, is orthogonal to the propagation vector, which is now described by the wave vector. The absolute value of the wave vector is our wave number. Yeah? So the direction of the wave is always described by the wave vector, which we call K. Yeah, and in this case, then we can express B by the electric field, where we have the cross product as before between the propagation direction and the direction of the electric field, which we can clearly also write as the cross product between EK, the unit vector of the propagation wave vector, and the electric field, here written as a vector, where we know this is pointing in B direction. Yeah, and what is also different, since we have now any direction, yeah, and not aligned, we have the dot product. We clearly need here a scalar. Yeah? We have omega t minus key z we had, where we have aligned our plane wave in z direction. Now it is going in k direction, so we have the dot product between r and k. Yeah, and that is illustrated here, where this plane means it's a plane wave, and in this plane we have the electric field and the magnetic field. And as we have seen here, according to our relations, we have used they are orthogonal to each other. Okay, so for a monochromatic plane wave, then in as a function of position and time, as written down here, we have to take the real part again of our complex ansatz or frequency domain ansatz, and so we have it as shown here, that we have a cosine of omega t minus now the dot product between this wave vector k and the position vector r, and the same we clearly have for the magnetic field, which we can express by the electric field. The amplitudes are quite similar. We just have to scale the amplitude of the electric field by the velocity of our electromagnetic field being C0. Okay, now let's have a look to the energy we have there. So we know the electromagnetic energy stored in this electromagnetic field due to this wave is 1/2 of E naught epsilon naught, which is the permittivity electric field squared, plus 1 over the permeability in vacuum B squared. And since we have this relation here, we can also rewrite this by the permeability and permittivity. And why we do it? Because we want to see this, that the electromagnetic field can be expressed here now in time domain in this sense by the electric field itself and our permittivity. Yeah, we know that, perhaps I write it here, that C0 is 1 over the square root of permeability and permittivity of vacuum. Our pointing vector is now written here with the electric field E and the magnetic field B. We have the scaling with 1 over the permeability, as you see, can be written now in this form, since we have this nice relation between V0 and E0 over the speed of the electromagnetic wave. So we get in now this relation. It is also important to clarify that this is again the propagation direction, should be, otherwise there's some mistake. So this pointing vector is pointing towards the propagation direction, and importantly is that we have here this velocity, because this part here gives us the energy density. And so we see that the energy density propagates with the speed of the electromagnetic wave. Computing the average intensity, which is, as we know, the average of our pointing vector, will give us time averaging. Yeah? So it is 1 over period and integrating over 1 period. We have here an energy density because we have these squares here, and that is what we know gives us, as we are used to also in circuits, to get here 1/2 of the amplitude squared. Yeah, we could also rewrite it by the root mean squares. Okay, so we have a very important, although these are simple steps, but a very important information now, that the energy also travels with the speed of our wave. Okay, so if we are in any linear media, yeah, with this index 0, that was always the indication that we are within vacuum. When we are in any linear media, then we know we have this constitutive equation where instead of the and isotropic, yeah, perhaps linear. Isotropic media, which is then expressed here by the relative permittivity and the relative permeability. Yeah, then nothing actually will change. Instead of epsilon 0 and mu 0, we will have epsilon and mu, which we can decompose in epsilon 0, epsilon r, and mu 0 and mu r, which means our speed of sound is now 1 over the square root of the permeability times the permittivity, and that we can simply also express by the speed of the waves in vacuum, approximately in air. And now when epsilon r and mu r are different from 0, we have to scale it by the square root of mu r and epsilon 0. Or perhaps you know that this actually gives you the refraction index, and that we denote by n. Yeah? So which is the square root of the relative permeability times the relative permittivity. So for most materials where we have propagation in a medium different from air or vacuum, we will have a permeability, a relative permeability being approximately 1. So it is, the permeability is just expressed by mu 0, which means then we can approximate the index of refraction by the square root of epsilon r. And everything what we have derived before in vacuum, clearly we just can apply here when we have any medium where epsilon r or mu r, but in most cases we will have materials where mu r is 1, applies. So we just have to substitute the values here by mu and by epsilon. Okay, so that we will then do next time. And we are interested in this case that we have a plane wave as showing here, traveling in z direction, but at an interface, the materials, both described isotropic linear, change their values in permeability and in permittivity. And we are interested what is the reflected wave and what is the transmitted waves. Yeah? That we will discuss for this simple case that the wave is impinging orthogonal to this interface. It can have any direction, yeah, as we have discussed in this case here. That will be a little bit more involved, but actually it is something which you have already seen and discussed in a little bit simpler case in optics, yeah, perhaps in school. But here clearly we have electromagnetic waves, we have all the background of fields and so on. Yeah, so we will discuss this, and then what will be also interested is to take into account perhaps that we have a conductivity which we have left out currently. Yeah? What is if this material has a electric conductivity, and there we will see that we will also get damped wave, and we will get a complex wave vector, yeah, which at the end, we always go to the time domain, will show us that we have an additional exponential term with a value which is real valued and which is in practice always negative in this sense, so that when the waves are propagating, the amplitudes decay. Okay, are there any questions? The chat. Okay. This is not the case, then thank